Let's see. Okay, we've got video, we have audio. I think everything's working. Let's see. Our test is going to be next Monday somehow. And if I'd like to have a 2-hour time block for the test this time. And I'll have to put out an announcement about that. But I'm hoping we can get by with just 1 2-hour block that day. We'll see. It just happened that all 3 of my classes are having tests next Monday. So you may be taking it at the same time as one of my other classes. I'm not sure just how we're going to make this work. I don't know if I can have 2 Zoom meetings open at the same time. So, but it'll work like the last tests we've done where you print it off at the start and then start working on it. Anyway, oh, let's see. We could probably dive into the topic since this is going to get recorded anyway. Today we're going to finish up that nuclear fission problem that we started on Thursday, and then we'll introduce the topic of capacitance, and so do a little bit with that. I can talk about capacitance when we get to it, so we'll just switch to this thing and hopefully nothing crashes. What we did last week was figure out the radius. We had a uranium-236 nucleus that fissioned into 2 equal sized pieces, each with half the charge and half the volume. This isn't quite realistic. Usually when these things fission, the 2 chunks are not identical, and then there will be stray neutrons as well. It's the 2 chunks that come out of this fission that are the source of the problem with radioactive decay that plagues nuclear fission as a power source. Nobody wants that stuff buried in their backyard. And these things are usually highly radioactive, and they'll have fairly short half-lives, which means they decay rapidly. And so that's one of the problems. When people talk about the long time that products or things from nuclear fission are going to be radioactive, they'll talk about time frames of 10,000 years and things like that. Actually, things that have half-lives of 10,000 years aren't so problematic because that means they decay slowly. It's this stuff that's the highly radioactive stuff that's the problem, and something that as a society we have not figured out just how to deal with it very well yet. So, but last week we figured out what the radii of those 2 chunks that come out of this sort of imaginary fission are going to be, and so now we have that to work with, and we'll see what it is we're supposed to do for the rest of this problem. In a simple model for the fission process, immediately after the uranium-236 nucleus has undergone fission, the daughter nuclei, that's these things, are at rest and just touching each other, and calculate the kinetic energy that each of the daughter nuclei will have when they are very far apart. Now, the assumption here is that the strong nuclear force is not going to be holding these daughter nuclei together. And actually, once something like this is fissioned, the strong nuclear force is so short range that it doesn't even reach all the way across a nucleus like this. And so it's actually a residual force of the force that holds the individual quarks together that make up the protons and neutrons. And while it might extend from some of the nuclei on this side of this daughter nucleus to some of the nuclei on this one, it won't reach all the way from nuclei here to nuclei over here, and certainly not from nuclei here all the way across to here. And so those will still be repulsed, though, by the electromagnetic force, which has an infinite range. It does get weaker with the square of the distance, but we're just going to ignore the nuclear force here and see what happens anyway. Now, we happen to know that these two spherically symmetric charges are going to be separated by twice their radius. So this distance here will equal 2 times the R final that we calculated earlier, which you can't see because I have it up there, twice this distance. So 2 times 5.9 times 10 to the minus 15th meters is going to be what that distance is. Well, two spherically symmetric charges like that are separated by that distance will have an electric potential energy, and we can call that U initial, the initial electric potential energy for this half, part B of the problem, and it'll be K Q1 Q2 over R. That's electric potential energy for 2-point charges. And in this case, the charges are identical. So we'll have here 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Some of this may be starting to seem repetitious. Each of these has the same charge of 46E. I think that's mentioned up here somewhere. Let's see, half the charge and half the volume. Half of 92 is 46. So 46 times 1.60 times 10 to the minus 19th coulombs squared, because there's 2 of them. And then that total distance, let's see, that looks like 11.8 times 10 to the minus 15th. Which is actually 1.2 about times 10 to the minus 14th. So that's the initial electric energy that you have. That will transform into kinetic energy. This is going to be, whoops, KE final, which is going to be 2 times 1/2 the mass of that daughter nucleus, I'll just call it M sub D, times V squared. And the assumption here that is because of the symmetry we have, that each of these will end up with the same kinetic energy. So we could figure out how much kinetic energy we're going to have released there. Let's see. Well, if I divide this thing by 2, that'll tell me the kinetic energy of each one of these daughter nuclei when they're far apart. Remember, the potential energy gets weaker with the distance, and so when these things end up being far apart, this will drop to a negligible amount. So the 1/2 mass of the daughter times V squared, and that's all we're after, is going to be this same expression here, which I'm just going to call U initial, divided by 2. And so we can calculate that, what that'll be. So 8.99, turn on calculator first. Let's see, square that. Okay, unit-wise, is this going to work? Coulomb squared, those go away. Newton meter squared over meters is just going to be Newton meters, which is a joule. So we will end up with that. And so far, I've only done this. I haven't divided by 2. So divide that by 2. And I would get an energy of 2.06 times 10 to the minus 11th joules. And if I convert that into electron volts, I'm just curious, I'll probably want to save the joules because I think the next problem means I'll need that. But if I multiply that by 1 electron volt over, let's see, 1.60 times 10 to the minus 19th joules, those two things are equal. And so I would get 1.29 times 10 to the 8th electron volts, which happens to be actually it's 129 mega electron volts is what it happens to be. 10 to the 6th of that is going to be the capital M part, and the other 10 squared will convert it from 1.29 to 129. So that's a fair amount of energy for one atom's worth of reaction. Typical chemical reactions, you may get on a scale on the electron volt amount for a chemical reaction, maybe a very few tens of electron volts at best for a chemical reaction. But this is mega electron volts, and that's what happens when you start mixing nuclei into things to produce energy. So that's what we have there. Now, the next part asks us to, in this model, the sum of the kinetic energies of the daughter nuclei is the energy released by the fission of one of those. So actually, we would want this asked the kinetic energy for each of the daughter. We would want the, wherever it went. Oh, it was in my calculator. Anyway, we'd want twice this amount. So about 4.12 times 10 to the minus 11th. Actually, we can probably only keep one significant figure. So 4.1 times 10 to the minus 11th joules would be the amount, the total amount released by that thing. So that's the energy released by it. But then it asks how much energy is released by the fission of 10 kilograms of uranium-236. So, holy smoke. Well, it's going to be a monster conversion energy or unit conversion problem. So, and here's the nuclear physics hieroglyphics for expressing that it's uranium-236. Well, I'd start with my 10.0 kilograms, and I would multiply that by, let's see, 1 mole over, now this is something, uranium-236 is going to have a molar mass of about 236 grams, and so I could write that Is molar AR for chemistry, or is it ER?
I think it's AR.
AR, okay, just like a tooth. All right. Which is 0.236 kilograms. And so 1 mole over 0.236 kilograms. And that'll tell me how many moles I have. And then I multiply that by 6.02 times 10 to the 23rd atoms. This is chemistry now, per mole. But what is that, about the first, sometime in the first month of a general chemistry class that you learn this stuff? I'm not sure, but I remember learning it in high school chemistry. Anyway, that'll tell me how many atoms I actually have. And then for every atom, I will have released twice this. So 4.1 times 10 to the minus 11th joules. So unit-wise, the kilograms go away, the moles go away, the atoms go away, and I just end up with the amount of energy released by that. And somehow I'm supposed to convert that to kilotons of TNT as well, which is the measure they use for the strength of bombs anyway. But let's see. Oh, that was my other conversion. All right, so 10 times, whoops, oh well, 10 times 6.02. And the only thing I divide by is 0.236. And hopefully we got this right. I get something like 1.0, close enough, times 10 to the 15th joules of energy. That's kind of a lot. Okay, and then if I express that in kilotons of TNT, and then I don't know, I think they just call it kilotons. So 1.0 times 10 to the 15th joules times 1 kiloton, and I'll leave the TNT off there, divided by 4.18 times 10 to the 12th joules. So let's see. And I get about, well, we can't keep that many significant figures, but it would be about 2.5 times 10 squared kilotons, which is 250,000 tons of TNT. So these things are very explosive. So in terms of this model, discuss why an atomic bomb could just as well be called an electric bomb. Well, it's the electric repulsion between those nuclei that pretty much drives this. It's nuclear forces that cause the instability in this nucleus and then the fissioning of it, but it's actually also the electric force playing a big role in the splitting apart of the thing as well. So that's something that happens with bombs anyway. Running fission things like this at a sustained rate is how a nuclear power plant works. And basically, you use the kinetic energy that's acquired by these things that come out of here to boil water is what you do. And the water turns to steam. You drive electric turbines with the steam and generate electricity that way. And I don't know anything about the design of the new nuclear power plant that the Grant County PUD is investing in. That'll be down on the Hanford Reservation.
I think it's supposed to be a pebble bed reactor.
Pebble bed, okay. I've read a little bit about those. There have been the nuclear accidents that have occurred so far. Well, the one in Japan, Fukushima, 10 years ago, I think. A little bit more than that now. But the accident was pretty much caused by a tsunami, which is a rare event, but maybe if you're in a country that's seismically active, don't put the nuclear reactors right next to the ocean. The one in Russia, this happened long before any of you were born, but I was in graduate school when this happened in the first half of 1986, and I can't remember which month it was. It was fairly early in the year, but it was a system that was designed so that if the power plant ever lost power, electric power, that the coolant couldn't be pumped into it. And you could have a safer design if you had it so if it ever lost power that the coolant got dumped into it, and so the reactions would cease. But that wasn't the way that one happened to have been designed. So we have learned from the mistake. A book I read one time, a long time ago by, I think it was by Freeman Dyson, said that the problem with nuclear power is that it was so complicated that it couldn't be built in a backyard by a hobbyist. And he compared it to motorcycles, that in the early days of motorcycles, this is the early 20th century, that they were terribly dangerous, but they were a whole lot of fun to play with. And there were people all over the world who were playing with building their own motorcycles. And over time, they actually came up with pretty safe designs for motorcycles, at least as safe a design as you can get, where you're not in an enclosure and you're going over 100 miles an hour sometimes. But designs for motorcycles have improved a lot, but they never had that luxury with nuclear power plants, that they're huge, complicated things. And maybe people have learned from some of the mistakes that have occurred with nuclear power plants and hopefully improved the design. They are one possible source of carbon-free energy, but they aren't without expense. They are expensive to build. And so you need to compare all the different options anyway. Okay, next thing I want to do is introduce the idea of capacitance. And capacitance, we have some capacitors in your electronics kits, and I'm not sure we're going to be able to do any experiments that'll utilize those things or not. But capacitance is broadly defined as the ability to store charge in the presence of a potential difference. Okay, now, if there is a potential difference, that means there's an electric field. And so somehow you're going to store charge in the presence of an electric field or a potential difference. The way that we measure capacitance, by the way, we use a capital letter C for capacitance. That's kind of nice. But it'll just be the amount of charge that is stored divided by the potential difference. And so the units of capacitance are going to be, we use the letter capital C for capacitance, but we also use it for coulombs. So I'm going to write out the coulombs over here. And it's coulombs per volt are the units that we use for it. I don't know of any standard or American unit of capacitance. We use the same, actually in electricity, we use metric units for it. We use volts, we use amps, we use coulombs and everything else in the American system. And for capacitance, we call a coulomb per volt a farad, and the abbreviation for it is a capital F. It's another one of those units that's named after a person, in this case, Michael Faraday. And so those are the units that we'll use. Let's see, things that don't have capacitance. Just a plain old wire. Okay, if you hook a wire up to a battery and try to apply charge to it, and this is the chemical symbol for a battery, the long line on top signifies the positive terminal of the battery, and the short line on the bottom signifies the negative terminal. And often you'll see it kind of written like this. So you have a set of those things, but it doesn't really matter that much for what we're doing. We're just imagining something here, but what'll happen in this case is that charge just goes through the wire, and the charge carriers in a circuit are actually the electrons. So they come off of the negative terminal, but for almost everything we do, it doesn't matter if it's negative charge going one direction or positive charge going the opposite direction. And so sometimes we'll just think of the charge going in this direction. And if it's just a wire, it just keeps going. There's no reason to stop it. The charges in a conductor, some of them are relatively free to move in the presence of an electric field. Not completely, that's what resistance comes from, but or the measure of the incompleteness of that is what resistance is. But this has no capacitance. However, you can have things that do have capacitance. And if you've got your positive terminal here and your negative terminal here, and you hook this up instead to a couple of flat metal plates that look like that, parallel metal plates, within a short time, you'll have the same potential difference across the plates that you have across the battery itself. And by short, I mean, if there's no resistance in this circuit, it's going to happen, you know, within like 10 to the minus 12 seconds or something like that. So a very short time. And that's what you'll have happening. And these things will have some actual capacitance to them. And so, in fact, the most basic design of a capacitor is called a parallel plate capacitor. And nearly everything else is just sort of an application of that, although you have to get kind of clever with it, because parallel plates by themselves are pretty hard to have very much capacitance with. So, the way we calculate the capacitance, if you're given something, is to imagine putting some charge on it and then calculate the potential difference that you get. And the ratio of the charge to the potential difference is what the capacitance of the thing is going to be. So if we imagine some parallel plates that have some charge on them, we can figure out what the we'll just imagine that here's our top parallel plate, and then here's our bottom parallel plate. And we're going to make some approximations here almost immediately. Let's just imagine that we have a charge plus Q on the top plate and minus Q on the bottom plate. And how much potential difference will we have here? Well, let's see. Let's imagine each of these has an area A. So we have that. And then the separation between the two plates is a distance D. And what are we going to have for a potential difference here? Well, let's see. I've already forgotten the expression, but the top and the bottom here is going to be a conductor. And so we'll have a conducting plane that's sort of infinite. Not really, but if you stay close enough to here. By the way, this distance D is going to end up being pretty small compared to the area. So if you get close enough to either plate, it looks kind of infinite. And so we can use Gauss's law to get the electric field of here. I'll look at a cross section of a Gaussian surface and try to figure out the electric field up here. And let's see, that integral of E dot n hat dA is just going to look, let's see, the electric field is going to point that way. N hat for the top plate does. The electric field is 0 inside here, and outside it points straight up, but the normal vector on the sides is perpendicular to the electric field. So the only place I have to worry about the E dot n hat part is on the very top, and that'll just be the surface area, which I'd better call A prime. This thing simplifies to EA prime. That's the area of my Gaussian surface, not the capacitor. And that will equal the charge enclosed over epsilon naught. But the charge enclosed is going to equal sigma, the surface charge density, sigma A prime over epsilon naught. And so the electric field will be sigma over epsilon naught. Whoops, that's not equal anymore. Anyway, the A primes divide out. So that's the electric field in here. And if this is the positive side and that's the negative side, the electric field points that way. Now, the total amount of charge that we have up here, Q, is going to equal sigma times A. So that's the charge on each one of these plates minus Q. This will be sigma plus on A. I'll have the same charge density on the bottom. So the minus Q is going to be sigma minus times A. And let's see what we can do with this. The capacitance of this device will equal the amount of charge on it divided by the potential difference. Okay. The potential difference between these two, when you have a uniform electric field, remember delta V in general is going to be, and we'll talk about the absolute value of it. It'll just be the absolute value of the negative integral of E dot ds. But when you have a uniform electric field, E dot ds, just take a straight shot between the two, it'll end up being, in this case, just E times the integral of ds from one side of this thing to the other, which is just the distance d. It'll just be ed. And the electric field is sigma over epsilon naught. So I'll have sigma d over epsilon naught is my delta V. Okay, well, Q was sigma times A, And on the bottom, I've got sigma times d over epsilon naught. I end up with, I'm going to bring this down, the capacitance is going to equal epsilon naught A divided by D. For a parallel plate capacitor with either air or vacuum would be kind of impractical. With an air gap, the capacitance is just epsilon naught A over D. So that's not bad. That's all it depends on, is how much area you have and the separation between the plates. And the smaller you can make that separation, the better your capacitor is going to be. So there we have it. Okay, let's suppose we have a parallel plate capacitor with circular plates of 8.2 centimeter radius and a 1.3 millimeter separation. So okay, here's 8.2 centimeters. And so that's just the radius of them. So I'd have to go all the way out to 16.4 here to get the diameter. So that's the diameter of our plates, and we'll have another one just like it that's 1.3 millimeters below it. So I'm not even going to try to measure 1.3 millimeters, but this is actually too much. That's more than 1.2 millimeters apart, but there's my top plate and my bottom plate. What's going to be the capacitance of that thing? Well, let's see. Epsilon naught A over D. Epsilon naught is at 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. Running out of room. Oh well, I've got white space I can run it onto. The area is going to be pi times the radius squared. So pi times 8.2 times 10 to the minus 2 meters. That's squared. And then the distance between them is just 1.3 times 10 to the minus third meters. What do we end up with for units? This will give us meters squared. That'll divide with that. So we'll have Coulomb squared per Newton. And then I've got a meter down there. Let's see. Take one of the coulombs and yeah, if I monkey around, got a meter over 1 on the bottom. Bring that up and I'll have a Coulomb squared per Newton meter. Or take one of those coulombs and take it to the bottom. Yeah, if you imagine a Coulomb over a Newton meter per Coulomb, if you inverted that and multiplied, you'd get up to here. But a Newton meter is a joule. That's a Coulomb over a joule per Coulomb, which is a Coulomb per volt, which is a farad. So we're there. We've got the correct units. And in this case, the capacitance is not going to be much. So times pi times, where is it? There it is. Square that, divided by, yeah, I get about 1.44. How much? I've only got 2 significant figures. So 1.4 times 10 to the minus 10th, and this would be Newton meters or coulombs per Newton meter per Coulomb, or farads. And the abbreviation for a farad is a capital F. So, or you could write that as 140 picofarads, which isn't, it's actually a common unit of capacitance. I'd have to dig out the electronic parts box to see what the capacitors in there look like for you guys. But that's not an uncommon capacitance, actually, although they're definitely not this way. One of the ways that they get clever about building capacitors is it would be really hard to have a very large plate here with a small separation like that. And if you want more capacitance, you'd have to decrease the separation. But what you can do is take a couple of metal plates like this and put something between them. Sometimes that something that you actually put between them will increase the capacitance. It's called a dielectric. And an early dielectric was wax paper. They used to put that between the plates of a capacitor. Various things like that. I've got an old capacitor out at school that has stuff like that. The layers themselves, the metal layers, are actually just metal foil, and they'll put the wax paper between it, and then, let's see, I think they may have had a layer of wax paper on top of the foil as well. They'll just roll it up into a little fairly compact thing. And then they, on this old capacitor, they put this fluid in there that turns out the fluid that they used to stick in those things is carcinogenic. And it's one of those things that it used to be in a lot of old electrical devices. And when it gets spilled onto the ground, it has to be cleaned up, because you do not want that stuff in your water supply. And so that's how things get designated as toxic waste sites, is when they've got some of those old electrical devices. But just watch out for it anyway. Now, this thing asks, what charge will appear on the plates if a potential difference of 120 volts is applied? Well, the capacitance is the charge per unit potential difference. And so we know what the capacitance of this thing is now. We just have to multiply by the potential difference that they're talking about, 120 volts. And so Q will equal our 1.4 times 10 to the minus 10th farads times our delta V. But remember, a farad is a coulomb per volt. And so 1.4 times 10 to the minus 10th coulombs per volt, and that's just units now, times a potential difference of 120 volts. And so I'll end up with a charge in coulombs here. And whatever that turns into, I get about, not a ton, but 1.7 times 10 to the minus 8th coulombs, or 17 nanocoulombs. You could write it that way. So that's how you would do such a thing. We'll probably stop with this one. The plates of a parallel plate capacitor are separated by 1.00 millimeters. How large must the plates be for the capacitor to have a capacitance of 1.00 farads? And if they're circular, what is the radius of the circle? Well, let's see. We've got, this time we know the capacitance. C is 1.00 farads. That will equal epsilon naught times their cross-sectional area divided by D, the separation. And so I know epsilon naught I'm given the separation, that's D there. And so all I don't know is the area of this. So that'll be dC divided by epsilon naught. Times 1.00. Let's see, it might be best to write this as maybe as a Coulomb squared per Newton meter. That's one of the possible combinations of units that'll give you the capacitance of something. Divided by, unless I made a mistake, 8 or epsilon naught, 8.85 times 10 to the minus 12th Newton meter squared per Coulomb squared. And let's see. No, I think I didn't get that right. Where was it? Let's call our farad a Coulomb per volt instead, and then see what we can do with that. All right. Well, never mind the numbers. Actually, they'll end up being 1 times 10 to the minus 3rd divided by 8.85 times 10 to the minus 12th. Which looks like 1.1 times, I can keep 1.13 times 10 to the 8th, whatever units squared we're going to end up with. It looks like I'll have a Coulomb meter over a volt, but a volt is a joule per Coulomb. And then on the bottom, I've got Newton meters squared per Coulomb squared. Let's see, just on top, if I work with that, flip it and multiply, I'll have Coulomb squared meters over a joule is a Newton meter. And then on the bottom, I've got, well, I've got that. But I can bring it up here and this is Coulomb squared per Newton meter squared. I had those units upside down. That was the whole problem. I was thinking of the units of our constant K, but K is 1 divided by 4 pi epsilon naught. So that's why the units have to get flipped. Anyway, I'll end up with multiplying that on top, Newton meters squared per Coulomb squared. There, I was afraid I'd have coulombs to the 4th. Didn't know how I'd get rid of those. A meter, a Newton, a Newton. Hey, it's meters squared. Okay. So if this thing happened to be a rectangle, you just take the square root of that to figure out how long it was on a side. There's the area of it. So then I'd only have 10,600 meters on a side. All for a 1 farad capacitor, or a 1 farad capacitor. So only that big, but that's if you've got a separation of 1 millimeter between them. I've got some capacitors at school that are 1 farad, and I can't see a little round object, but they're only about this big around, and they're about maybe that thick. Something like that. But inside that little mint-sized object. It's about the size of a Girl Scout mint, I guess. There's something in there that somehow gets a whole lot of area to separation, a very large number for that. And one of the ways you can do that is to use a plastic film between the two conducting plates, or something like Teflon maybe. And so that's a way that you can bump it up when you're dealing with things like that. I think that's all I had for starter problems today, just kind of getting our feet wet with capacitance. And tomorrow we'll look at some other geometries for a capacitor besides the parallel plate capacitor. We'll look at a cylindrical capacitor. With those, you actually have a capacitance per unit length. And then last year, I had some lab money left at the end of the year, and so I ordered some large capacitors at the end of the year, assuming that I'd be able to use them this year for maybe experiments in class or something like that. And I was wrong about that, but I may run out to school today and record a little bit of video of things that you can do with capacitors and see just what we can do anyway. Any questions on that? I still see we're recording, I hope. Again, test next week on Monday. I've posted a new homework assignment that has questions on electric potential and a few on capacitance as well. And that will be due, I think I've got it due next Monday morning, actually, like 9 a.m. or something like that. I can't remember, but that's so you'll do it before the test, because the whole point of it is to help prepare you for the test. So we'll have that going on, and we'll have possibly a review on Thursday during the regular class time, and we might be able to have one on Friday morning as well if people are interested in that. We'll see, or if you couldn't make a Thursday morning one, might be able to have one later in the day on Thursday as well. So other than that, I think we'll stop there, and I'll see you tomorrow.